Alright guys, welcome to 5.3 Conditional Probability and Tree Diagrams. This is a 5.3 part 1, just so you know. There's not really a ton new here except for this whole idea about tree diagrams. It's a different way of looking at conditional probability, but the nice thing is everything else is pretty much review. So what I'd like you to do is make sure you're paying attention to your homework assignment and you've got your EQ down. Let's get going. So first couple of examples that we have, these are directly from your notes, okay? This table you have on your half sheet examples will revisit this same prompt that we had last time, but we'll go through this real quick because this is just really review. So what's probably that a person is a graduate and owns a home? That's an intersection probability, which means we are looking at the intersection between those two, and that we have answered yesterday 221 out of 500. Not a big deal. Next one, what is the probability that a person is a graduate given that they own a home? So now we are introducing these ideas of conditions. So when it says given they own a home, we have to assume that the only ones we're looking at now are home owners. So how many homeowners do we have? This number right here, 340. That becomes our denominator. So of those 340, how many are graduates? 221. The next question seems like it's the same thing, but it's not. We do have another given, but now we are saying what is probably the person owns a home given they are a graduate. So now we are reducing our population from the 500, not even looking at those 340. We're now looking at the 310 that are high school graduates. So we have 310 in our denominator and 221 is still the numerator. We're still looking at that intersection between those two for all of these. But as you can see, very different probabilities. And whenever you change it to a conditional probability, introduce this given, you're actually shrinking down your population and making your probability larger. So, that brings us to our definition of conditional probability. We write it like this. Probability of A given B. And there is a formula that we will come back to later that is this. Probability of A and B divided by the probability of B. You can think of it also in this way. It's the probability that both events occur, the intersection of those events divided by the probability of given, which is exactly what we did there. We looked at our given first, the denominator, and then we looked at the intersection between those two things. Other ways we can think about it is that we read conditional probability, as if B happens, then A happens. We can think about these as if-then statements quite a bit and makes it easier. Another way I like to think about this that's going to help me get the fraction right, if I were to turn that vertical bar, just tilt it a little bit, I would have A over B, and it shows me that this is my given, and the given part should always be the one that's going to go in the denominator. So let's go ahead and take a look at our half sheet example now, and we will answer a couple of these questions, and then I will try and let you get to answer a couple of the other ones on your own. All right, so if we know that a person owns a home, what is the probability that a person is a high school graduate? So again, we see these if-then statements. So if we know somebody owns a home, we are looking at this cell for our total, those homeowners, 340, and then how many of them are high school graduates? That's this amount right here, 221. So we would only be looking in that row. Okay, so the next one we're looking at, given that a person owns a home, what is the probability that the person is not a homeowner? So again, we have this condition, given that they own a home, tells us what our denominator should be. We again are looking at those 340 people that own a home. Now, the cell we are interested in are those that are homeowners that are non-graduates. So we're still looking in that row. We're excluding everything just to the row of homeowners to find that value. Okay, 119 out of 340. Next, notation. We got to be comfortable with this and remembering that which one is actually going to be our denominator. So, probability that somebody's a graduate given they do not own a home. H complement is non-homeowner. So, the non-homeowners are the ones that I want to be paying attention to as my denominator. So, how many non-homeowners do I have? 160. Out of those 160, how many graduated from high school? 89. Okay, next one. given that somebody is a non-homeowner, again, the same 160, what's the probability they are non-graduate? That's the 71 out of 160. So I'll give you a second to finish E through H, try and get those done on your own, and we will check with everybody in just a moment. All right, so here are the last few from this set. Check them out. Check with your neighbors, talk to each other, help each other out. And then what I want you to do is take a look at the next example that you guys have on your half sheet. This one revisits the landlines and cell phones. And then you'll be able to come back and take a look and check with my answers. What I want you to do with that one, though, is actually make sure you go through and do the division. We don't usually like to see decimals in fractions, so go ahead and actually carry out the division for those and get a decimal rounded to 2 places, 2 digits, please. All right, so here are the solutions that you should have for A through D and E through H. If you have any questions, feel free to post something on Google Classroom, or we can talk about it the next time we see each other. Please make sure before you do that, you check with your neighbors. I think everybody in the room should be able to get a hold of this pretty quickly. All right, so now when we actually turn it up a notch and we start taking a look at tree diagrams, this is something that we want to take a look at when we are looking at things that tend to happen in sequence, or one thing happens right after another, so really true if-then statements. In a lot of ways, these can be faster to create and interpret than a two-way table can. However, a two-way table may be better, especially if your data is in counts or numbers, like the first example was, rather than in percentages. Percentages tend to lend themselves to tree diagrams a lot better. Okay, so with these, we just want to again think about this in a very logical, straightforward way. So let's try and do that and pay attention to the language that we use. The language is key to understanding tree diagrams. So let's take a look at this example. Shannon hits the snooze bar on her alarm clock 60% of school days. Today, I did not hit my snooze bar. Go me. Hopefully you didn't either. But if she doesn't hit the snooze bar, there is a 90% chance that she makes it to class on time. However, if she does hit the snooze bar, there's only a 70% chance that she makes it to class on time. So if we were to randomly select a day, what is the probability that Shannon is on time for class? Okay, so when you first read through this, your gut might be just to say, well, I can take 0.9 and 0.7 because those are the times when we say that she's on time. But what happens if we add those two together? 0.9 plus 0.7 gives us 1.6. Hey, we know that can't happen, right? That's a bad thing. Probability can't be more than 1. So let's get rid of that and think about this in a more logical thing, right? We've got two essential variables that are happening. She hits the snooze or she doesn't, then she makes it to class on time or she doesn't. Okay, so in that case, we want to break this apart because this does follow a logical sequence, right? And so what happens first? Her being on time or her hitting the snooze? Well, first thing happens, she wakes up and she either hits the snooze or she does not. So we'll call hitting the snooze S, and then not hitting the snooze S complement. Okay, and then we said that the probability that she hits the snooze on any given day, given school day, is 0.6. That means that she has a 40% chance or 0.4 likelihood of not hitting the snooze. Now, if she hits the snooze, she has two possible outcomes that happen next. She is on time for class, or she is not on time for class. So we'll call that OT for on time and OT complement. And the same thing happens if she hits the snooze, or if she doesn't hit the snooze. She is still going to be on time, or she is not. There's no other way we can really break it down. Okay, so let's use this to try and think about it. If she hits the snooze, what's the probability that she's on time? Did we get that probability in the prompt? If she hits the snooze, what's the probability that she's on time? We were given this information. It was 0.7, right? 0.70. I'm going to go ahead and add the 0 to each one of these just to be kind of consistent. Okay, so 0.70, which means what's the likelihood that if she hits the snooze, she does not make it to class on time, 0.3. It's just a complement rule. We're just subtracting. Now, if she doesn't hit the snooze, she was a good, vigorous young go-getter. She wakes up right at the sound of her alarm. That is a 90% chance then that she made it to school on time. However, there was still a 10% chance that she would be late. Okay, so paying attention again to the language was really helpful for us here. What we wanted to notice was that everything in this, at the end of these branches, were all of our conditional probabilities. If she hits the snooze, she has a 70% chance of making it to class on time. Okay? So what's nice is that if we're given conditional probabilities, then tree diagram lends itself to using it, right? But that's not the question we want to know. We want to know on any randomly selected day, what's the probability that Shannon is on time for class? Well, we take a look at this. This also tells us all of our possible outcomes, right? And what are all of the outcomes in which Shannon is on time for class? If she hits the snooze and she is on time. If she doesn't hit the snooze and she is on time. Well, the problem is this still doesn't help us yet. We have to think about it in one more way. So, we still look at this. This 70% is not 70% of 100%. It is 70% of 60%. So, what that's going to actually tell us is the probability that Shannon hits the snooze and she is on time. What happens here is that 70% of 60% of all instances relates to her being on time from hitting the snooze button. Okay? So by multiplying these two values, 70% of the time, or 70% of 60% of all instances, Shannon is on time. 70% times 60% is 0.42 or 42%. Now the same logic can be applied here. 40% of the time, she does not hit the snooze. 90% of those 40% of times, she still makes it to class. So the probability that she does not hit the snooze and is on time is going to be 90% of 40% of the time. Now, when you multiply these together, we get 0.36. And if you take a look, there are no other outcomes in which we have Shannon being on time. These are the only two ways that we can have it. And these are mutually exclusive events. They can't happen simultaneously. So that means we can add the two probabilities together, and that gives us our total probability that Shannon is on time. And we have now answered our question. So a really cool thing that happens with these is, again, we didn't use any formulas. The only thing we did was we used some logic based off of language to understand that at the end of these branches will always give us our conditional probabilities. And then by working backwards, by understanding that if we can think about 70% of 60% of occasions represents her being on time, that word of, using that word of, means multiply. Once we understood that, we were able to calculate the probabilities that we need. Okay? So, let's say you hate tree diagrams. This doesn't make any sense at all. You can still make a two-way table from this as well. So let's take a look at what making a two-way table is going to look like. Okay? So if I want to make a two-way table, we still break it down the same way, that Shannon hits the snooze or she does not. And then she is on time or she is not. We have our total column and a total row. And the only thing I know right off the bat is that these are all in percents. So I'm going to have 100% in the bottom right. Okay? We'll go ahead and make our two-way table. You may have to do this on a separate sheet of paper, but I would like you to, just so you can get the feel for how this works. Because the two-way table is a really great tool, and I prefer it in a lot of ways to the tree diagram. If you hate the tree diagram, you just want to use two-way tables, go for it. Let's go ahead and use it. So, what we know just from the prompt was that we have 100% of all situations, and 60% of the time, Shannon hits the snooze. 40% of the time, she does not. The other information isn't really told to us. Okay, we have to kind of infer a couple of other things to figure this out. And this is where it's difficult to make a two-way table unless you have some kind of base understanding of what is really going on in the situation. So, how we can make this work at least is saying, well, I understand that 90% of these 40% is representing her being on time. And then the same token here, how we can end up getting this value here, the on time we have 70% of the 60% of the time gives us the 42% value. Then we can go ahead and fill in the rest of these values the same way that we did before. We add these two to get our total for her being on time. That means that if she's on time 78% of the time, she is late 22% of the time. Okay, 36% and 0.04 will represent when she is not on time and didn't hit the snooze. Next one, 42%, 60%. I am missing 18% that are unaccounted for there, and we can make a two-way table that way. Okay, so definitely ways that you can still make the two-way table and then answer other questions, because now, once we have the two-way table, we don't have to rely on the condition of Shannon hitting the snooze button. We could look at the condition of her. Let's say we know she was on time. How likely was she to hit the snooze button? We could answer questions like that now. All right, so one more example I want to try and do with you guys, or at least get you set up, and then I want you to finish the remainder. Okay, so with this one, take a moment to yourself, read through this prompt, and I want you to highlight the things that are important. Okay, so if we were to highlight the things that are important, again, you may need to pause and reread. I'm going to go ahead and highlight them now. If you need to pause because you want to do it, go for it. So I see 17% were classified as light media users, 62% were moderate, and 21% were heavy media users. And then I see this big phrase here, of the light users, 74% were described as having good grades. Why I highlighted of here is because I want to make sure I recognize that as being a conditional probability. 68% of the moderate users and 52% of heavy users describe their grades as good. Okay, so now instead of actually just highlighting, I actually want to write out what the individual probabilities are that I know. It's just going to be an organizational tool for me that's going to help. So I'm going to define the light media users with the letter L, and that's 0.17. My moderate users, I will define with with M, and that was 0.62. And then my heavy users with H, and that was 0.21. The next thing I knew was some conditional probabilities. So I had to recognize those as conditional by the word of the light users. Those that said their grades were good, 74%. Given that they were a moderate user, those that described their grades as good, that was 68%. And given that they were a heavy user, 52% described their grades as good. This is not required in any way, but I find it hugely helpful for us to organize our thoughts and start to make the tree diagram. So now what we want to recognize is that the condition is always going to come first in our tree diagram, and we have three conditions actually this time. They are light user, a moderate user, or a heavy user. Okay, I put the probabilities at the end of each of these. And then we can break this down. You can use good complement, or I'll use good complement this time. So good complement and good. Again, we had good grades and not good grades. Good grades and not good grades. So making the tree diagram here, we see that there was a 74% chance a 68% chance, and a 52% chance. Good complement then, complement of 74% is going to be 26%. It's just subtracting from 100. 0.32 down here, and then 0.48. So hopefully you start to recognize that these again are all complement rules. These guys at the end of every branches that you have should always add up to 100%. Okay, so next thing we want to take a look at is actually answering the question. So the question that's on your half sheet here is, what is the probability that somebody gets good grades? Well, we have to look at all the different possible ways in which somebody could have good grades. Light media users, moderate, and heavy. So to do that, we have to say 74% of 17% of our kids said they have good grades. 74% times 17%. Another 68 times 62, 68% of 62. And then 52% of 21% said they had good grades. When we multiply all of these together, go ahead and punch it into the calculator for yourself, and we should get, rounding to 2 decimal places, 0.66. That is the probability that somebody has good grades. Now the next question is a little bit tougher to do when we don't have that two-way table. The next question, question B, asks us, given that somebody has good grades, what was the probability they were a heavy media user? Well, unfortunately, I don't have any information here with the good grades part. So this is where we have to understand that definition of conditional probability. So if we go back and take a look at what the definition of conditional probability was, the formula that we had, it was right up here. Probability of A given B is equal to probability of both divided by the probability of the given. Okay? So when we go back here, what's the probability of both of these events? Probability of H and G occurring divided by the probability of the given, that they had good grades. That's what we want to know. Well, this we just found, right? Probability of G we just found was 0.66. So we know our denominator. How do we find H and G? Well, that was this result right here. 0.52 times 0.21. When we multiply the two connecting stems or branches of a tree diagram, that gives us the intersection probability. So now we can find the probability of H given G by doing this. And when we multiply those together, I believe we get 0.17 as our probability. Now, that is not at all really all that intuitive. So what I'd like you to try and do, though, is try and make a two-way table of this, and then you can check with mine, and we can look at it and see, hey, did we get 0.17? Do we get the same thing? Okay? So you can take a moment to do that, and then check my two-way table. All right, so here's my two-way table that I made. Again, I have to use some of that understanding of how to get the intersection probabilities, that I have to multiply the corresponding conditional probability with the given probability to find that. You're not going to be able to make a two-way table if you don't understand that from conditional probability problems. So you only need to find one. You only need to find one row or one column, and then you'll be able to figure out the rest from there. Okay, so I figured out this one column here and added those up to get my 0.66. Okay, now I take the complement of that. If there were 66% said they had good grades, that means 34% said they didn't. And then I was able to work from here. If 11% said they had good grades, 10% must have said no to get 21. 42 and 20 would make 62. 13 and 4 would get 17. When you first start out, this is all you are given. So you have to try and work backwards and understand this relationship here first before you can do that. Then it becomes really easy for us to figure out what's the probability that given somebody has good grades, they are a light media user. Well, we know our denominator is 66, and then we have the 0.11 divided by 0.66, which again is going to give us 0.17. And that is that. So there's one other example I'd like you guys to try and tackle. If you still got time, please talk to each other, help each other out. And your assignment, I'll have the textbook available to you that you can take pictures if you need to. Have a wonderful day, you guys. Thanks for watching, and I will see you on Friday.